So for our notes, the way our lessons are going to work, I have our notes posted on our weekly agenda on Canvas. So this is up to you. If you want to have those notes up and you kind of go through and jot things down as I talk, that's good. If you'd rather have like a blank sheet of paper or whatever, I mean, you do what works for you. However, like, make sure that you're focused, you're attentive, and that you're kind of engaged with what we're talking about here, okay? So, kind of a weird way to start our first lesson with this, like, looks like a 1970s psychedelic acid trip kind of a thing here, right? We have clutter. And then Albert Einstein said, out of the clutter, find simplicity. So when you first look at this, you see clutter. You see colors, you see all sorts of things going all over the place. But when you start to focus in a little bit more, you start to see something. Tell me what you see in this picture.
A deer.
A deer? Yeah, that kind of stands out. We got this deer and the antlers right there and the legs down there. What else? What was that? Oh, somebody in the hall.
At the bottom, there's a fish.
Yeah, you got this like fish jumping out with the eye and the mouth, and oh, maybe these are bubbles coming out of his mouth right there. Yeah, we see like this kind of like a rainbow river or something going along, and then a sun there, flowers. So I use this to kind of demonstrate how we visualize data. Because when you have like raw data, okay, let's say you're doing a survey, you're collecting data, people's opinions on things, that can be very dry, that can be very bland, especially if it's in some big table. It's difficult to see what's actually going on in that data set. Okay? But Einstein said, out of the clutter, find simplicity. Find a visualization to let this data show you what's going on. Okay? What are the trends that are happening? Okay? And that's what we're looking at today. Okay? We're picturing these distributions with graphs. Okay? Now, we're using our visual techniques to demonstrate our data sets. And we're going to be looking at the different types of data. We have categorical and quantitative variables. So that's one of our key targets here. But from that definition, we want to be able to choose an appropriate display for each of those types of variables. Now, a lot of what we're talking about today, I know that you've seen it before. Okay? Bar graphs, pie charts, stuff like that. Okay? You know the tools at your disposal. We're going to be doing an activity next week that uses the technology that we have available to us to help create those. But for today, it's important to think about why you would use one display over another when you're trying to convey your message about the data. A little more detail about what we're talking about here. All right. So I had said that statistics, it's a tool for helping you go through information and draw conclusions. Okay? A little bit more formal of a definition here. Okay? A science that involves the extraction of information from numerical data obtained during an experiment or from a sample. Okay? It involves the design of the experiment or sampling procedure. We have entire chapters that are based off of just sampling procedures, how to get a good sample. Okay? The collection of that data, the analysis of that data, and making inferences about that population. Because again, if we want to observe a trend about what's happening like nationwide, we don't want to have to look at and measure all 330 plus million people in this country. We want to use a sample in that smaller size to accurately reflect what's happening in the population as a whole. Yeah? but we're using that sample to help us. In short, statistics is the science of data. Now, I call it data, okay? My wife, who I mentioned is also a stats teacher, she calls it data. I mean, it's a very contentious part of our relationship here, but I don't care what you call it. A data set contains information about a number of individuals. Okay? And the first step in dealing with data is to organize your thinking about the data. So we see some terminology here. I'm not going to spend much time on it because it's pretty straightforward, and I'm not going to assess you on that. Okay, I'm not going to ask you is this an individual or is this a variable? Okay, but the individuals are the objects that are described by a set of data. Okay, typically it's people. Okay, it could be animals, could be things, whatever. The variable is the characteristic of that individual. Okay, so the individuals are people in this class, and we're looking at hair color. Okay, brown, blonde, black hair, etc. Okay, the hair color would be the variable. The individuals are the people. We can take different values for different individuals. Here's another example here. We're talking about racehorses. We have the horses and their names. Okay? The individuals here are the horse and all the characteristics of that horse. Okay? But the variables are the name, the breed, the selling price, and the stable for that horse. Okay? Different ways of breaking it down. There's a little extra fluff in here that we don't need. Okay, so categorical versus quantitative. This is a big idea here. Yeah? Categorical data places individuals into one of several groups or categories. Okay? It has a label that goes with it. The hair color that I was talking about, that is a categorical variable. As opposed to a quantitative variable, there is a number, there is a value that is associated with that. Okay? It takes numerical values for which arithmetic operations make sense, usually recorded in a unit of measurement. And so we see the breed of the horse is a categorical variable, the selling price is a quantitative variable. Usually it's as easy as this is a number, this is typically not a number. However, that's not always the case. For example, I know you've always taken those surveys that are on a 1 to 5 scale. To what extent do you agree? Yes, technically those are numbers, but they are serving as labels. They are serving as categories. Okay? So every so often you might have numbers that are kind of disguised, or they are disguising categorical variables. I'll usually mention that as when they come up, and you'll see that from time to time. Is the variable monthly rainfall in Michigan, is that a categorical or a quantitative variable?
Categorical.
Because you're measuring this.
Quantitative.
It'd be quantitative. How much rainfall do you get? Is there 12 inches of rain? That would be a quantitative variable. Okay? Don't want that. Don't need that. Now, to look at the picture of what's going on, we want to look at the distribution when we're dealing with quantitative variables. Okay? This distribution tells us what values a variable takes and how often it takes these values. Okay? Now you can get these values a table, a graph, or a function. Okay? Typically, we're not going to get them from a function. Okay? We'll either have our data on a table or on a graph. And the values of a categorical variable are labels for those categories. The distribution of a categorical variable lists the categories and gives either the count or the percent of individuals who fall into categories, okay? So back when we're talking about quantitative, you're talking about like rainfall per month in Michigan, okay? You have a value that is associated with each item, okay? January's rainfall, February's, March's, etc. But if you're talking categorical, now you're talking about how many individuals fit this category. Okay, going back to our hair color. Let's say there are 3 individuals with blonde hair in this class. We could represent that as a raw number, or, like I had said yesterday, maybe a better way of representing it is with a rate. Okay, and say something like 10% of the individuals in this class have blonde hair. Those are categorical measures. So we have certain displays, certain types of graphs that are designed for these different types of variables. The categorical variables, pie charts and bar graphs are the 2 big ones. Quantitative variables, histograms, and stem plots. Okay. Now, categorical, a pie chart, it has the big kind of asterisk behind it that you have everything adding up to be that part of a whole. I mean, I know you've worked with pie charts before, circle graphs. You have to have that part of a whole idea that goes with it. Bar graphs, they are, well, I'll get into them. They're very easy to work with. We have an example of a data set here. College freshmen were asked what they planned for their major. And we have this table of data that's listed as a percent. Okay? Is this categorical or quantitative data? Do we have labels, or do we have like measured values? If I asked you not as a freshman, but as a high school senior, like, what do you plan on majoring in? Are you going to give me a label, or are you going to give me some measured number?
Categorical.
Yeah, this is categorical data. Okay, arts and humanities, biological sciences, etc. And our values, our measures, are in percent. Okay, little rounding error that they add up to 101 or 100.1%. Not a big deal. So we have that part of a whole idea going on here. So a pie chart is a good representation of this data. So we see, like in this slice for business right here, we had 14.5% of those surveyed majoring in business. So 14.5% of that circle is business. You go flashback to geometry. If you were to draw this by hand, which we never do, you'd take your protractor out, 14.5% of 360 degrees. That is the angle for that slice right there. Okay. We're not going to be drawing these by hand, don't worry. Now, here is that same data set expressed as a bar graph, 2 bar graphs actually. So remember that the pie chart, you have that part of a whole idea. Here, we have the height of the bar representing that percent, and then we have all of these labels going across the bottom, the x-axis, and the height of the bar is that percent. Which of these is a better representation? Is one better than the other? I mean, the difference here, these majors are alphabetized on this left one. Here, they go into descending order. They start with the highest, and then they fall down and to the lowest. Well, part of it depends on what is the message that you're trying to convey. And there's no right or wrong answer that like it should always be alphabetized or that it should always be in ascending or descending order. If you're trying to show like the drop off, like this might be a better way of showing it If you're talking about the most popular majors and the least popular, it's very easy to identify that in this second graph. But if you had a huge list, I mean, this isn't terribly big, but if you had a huge list of majors that you were specifically looking for a particular major, then the alphabetized version might be better. Okay? So there's no like right or wrong answer, like what's the best display? Think about the message that you are trying to convey with your data and what technique lends itself to that. Would it be the pie chart? Would it be this bar graph or that bar graph? We have a breakdown of 4 grades and the makeup on the first day of class for I think this is a college statistics course here. And what is the makeup of those students? Freshmen, sophomores, juniors, and seniors. There are 43 total students in this course. We have the count, we have the percentages. Just based off of this, and not really knowing much about what you're trying to say, what do you think would be a good display of this data? Yeah. Probably a pie chart, because you have that part of a whole idea going here. Everything's added up to approximately 100% there. Okay, pie chart's probably the best way to go, not knowing much about that situation. Okay? The bar graph, okay, you lose out on that idea of part of a whole, okay? But still a possible and accurate display of the data. Now, you can get more out of a bar graph if you want to. Okay? So we have a question here. What sources do Americans aged 12 to 24 years use to keep up to date and learn about music? Now, admittedly, this is about an 8 or 9-year-old question here and responses. But we have our choices right here, everything from radio through Spotify, iHeartRadio, Sirius XM, that sort of thing. And on this bar graph, we have the percent who have used that source for learning about new music. We have that up here, and these are clearly put on there in descending order. So friends and family, word of mouth, that's the highest, going all the way through music blogs is the lowest. Okay? This would be a bar graph. Why could a pie chart not work in this case?
It doesn't add up to 100%.
Yeah, they don't add up to 100%, which means that if you were participating in answering this question, you could have answered in multiple ways, right? You could have said friends and family, radio, yeah, any of the above that apply to you, that works for this question. So that eliminates being able to use a pie chart in this case. This question, bar graphs are more flexible than pie charts. Both types of graphs can display the distribution of a categorical variable, but a bar graph can also compare any set of quantities measured in the same units. I didn't really get into that, but that's a good segue here. That is a true question. Okay? Because, I mean, going back to our previous example there about learning about new music, if we had this as one question and our bar graph is in blue, okay, but I also had maybe some of these would also apply to how do you learn about like new television or whatever. I mean, you could maybe adjust some of these, but friends and family would still be there. TV in general, Facebook would be there, okay? Maybe iTunes or music store, that sort of thing. You could measure something else with that same bar graph and put it in red, so you have like a double bar graph going out of here. So the blue bar would represent for music, and the red bar would represent learning about television from your friends and family. Because you're measuring with a percentage who have used that and you can make that comparison side by side. Maybe that's a message that you're trying to convey. Okay? You have more flexibility with what message you're trying to get across when you're working with a bar graph. We had said this: the order of categories on a bar chart should only be arranged alphabetically and should never be rearranged by height. That is false. It depends on the message. Okay, so bar graph, pie chart, those are for categorical variables. For quantitative data, we have a couple other options. Okay? Histograms and stem plots. Now, a histogram shows the distribution of a quantitative variable using bars whose height represent the number of individuals who take on a value within a particular class. Okay? A histogram looks an awful lot like a bar graph. I will admit that. Does anybody know, or maybe I know sometimes like an 8th grade teacher like really drove this point home. What is the difference between a bar graph and a histogram? I've heard people say that, like on a bar graph, the columns don't touch each other, and on a histogram, they do touch each other. That's a okay way of looking at it. Okay. Sometimes you can have some inconsistencies with that, but there's a better answer. Okay. The bar graphs represent categorical data. So everything that you have on the bottom there coming out of each bar is a category. It's a label. Okay? You learn about this music from friends and family, or you learn about it from the radio, or whatever. With histograms, you have quantitative data, and everything falls within boundaries, numerical boundaries. Okay? So with this histogram, I'll come back with stem plots in a second. But you take an appropriate quantitative variable and split it into different regions. You're dividing the possible values into classes, or what they are called. Now, they do need to be the same width. You can't have one that's like really wide and then another that's really narrow, because then you're misleading and you're skewing the data. You're counting how many observations fall into each of those intervals. And now you could have the raw number as the height of that bar, or you could have it as a percent, and you're drawing this picture representing the distribution. The bar heights are equivalent to the number, the percent of the observations in each interval. So here, in this histogram, we have data collected from, I think it's different universities, about the freshman graduation rate. Okay? What percentage of their freshmen go on to graduate, okay, from their colleges? So we see that these are all individual, these are actually states. Okay, so you're looking at the individuals within the states. So the individuals are the number of states that fit into those categories. Okay, so there was one state that had a freshman graduation rate between 55 and 60%. Okay? 60 to 65, 65 to 70. Notice the width of these intervals. It's consistent. And also pay attention to those boundaries. Okay? What if you had a state that had exactly 70% graduation rate, freshman graduation rate? Okay? It would go into this column right here, the 70 to 75, because we have the less than 70. We're going to talk a little bit about that next week when we use technology to help demonstrate or to create a histogram for us. Now, you might be asking, like, how do you determine the width of those intervals? We have little techniques. One rule is to calculate the square root of the sample size and then round up. Okay? That's one way. Sometimes we have logical boundaries. Like if I wanted to make a histogram that talks about the distribution of test scores across the class, well, I think my logical classes or boundaries would be like 90% and above, okay? 80 to 90, 70 to 80, and so forth. Those are kind of the customary intervals that we have for our grading scale. All right. Make sure that all of the individuals fall into only one of those boundaries. Okay, so pay attention to those boundaries themselves, okay, that you're not counting it twice if it's exactly on there. This was a collection of data from Virginia Commonwealth University that had the weights of people in their 1997 spring statistics introductory to stats class. Yeah. So we had the weight of all of these individuals. Here's that raw data. You could split it up into this is called a frequency table, where you're looking at the boundaries of those classes, 100 to 120, 120 to 140. So we have about 20 pounds as the width of our intervals, and you're counting how many individuals fall into each of those. They determined this width of 20 by taking the sample size of 53. They took the square root at 7.2, and they decided to round that up to 8. Okay, so 8 intervals is what they decided. They have that laid out here. And then they used the range, which was 260 was the max, down to 100, that was the min. So 260 minus 100, 160. 160 split 8 ways, gave them that perfect width of 20. Now that's kind of like a best case scenario. Rarely does your raw data work out that nicely so that it's like 28. You can see everything right there. Here's what that histogram would look like. Notice that we have a little bit of a standout right here. This is a higher weight, only one individual. Also notice that there was nobody in this category, okay, and that space being absent right there makes this stand out even more. So when you're looking at a histogram, you're looking at the overall pattern of that data. Okay? I said that the purpose of one of these graphs or one of these displays is to help you get an idea of the distribution. What is the message that's trying to be conveyed from that data set? Okay? Are there any striking deviations from that pattern? We can describe the overall pattern by the shape of it. Okay? Where is the center of that in terms of like, is the median the center, the mean? And also looking at the variability. Is everything really compacted right around that center, right around that mean? Or is that data very spread out and scattered? And coming back here, we can see that we've got a little bit of a peak. This definitely does stand out here, possible outlier that we will talk about in the future. But right here, we have a little bit of a discrepancy. We set it's kind of like 2 peaks in a valley. That's kind of a red flag for us that maybe we're combining individuals into one set that should really be looked at separately. What might those 2 types of individuals be in this case?
Male and female.
Yeah, male and female. Okay? Typically have different like average or normal weights. Okay? So we probably see a peak for male weights and a peak for female weights that might be explaining this valley in the middle right here. All right, sometimes we'll see variability referred to as the spread. An important kind of deviation is an outlier. An outlier is an individual that falls outside the overall pattern. This is kind of like a very general definition of this term. that we're going to get more precise with a mathematical interpretation, like you calculate, is this an outlier or not? Okay, we'll get to that. The most common type of distribution that we will be seeing and be working with is a symmetric distribution. If the right and the left sides of the graph are approximately mirror images of each other, okay, they're bell-shaped, okay, we'll see that term a lot, they are symmetric in their distribution. Now, a distribution has skew, okay, if it's a bulk of the data in one end or the other, okay, and you have a little bit extending out to one side. Okay? The way to think about this, the direction of the skew is the direction of the tail. Okay? Let me write that in here, the tail. So this data set right here is skewed to the left. We have most of the values really high, okay? But then a couple of smaller values that are pulling this away from being a symmetric distribution. Okay? This tail extends to the left, so it is skewed to the left. This tail extends to the right, it is skewed to the right. Okay? I always say there's like an example of a data set that's skewed to the right. When LeBron James was playing for Cleveland, you know, he's like Ohio born and raised, and he was born in Akron, Ohio, and when he's making his tens of millions of dollars, he decides to build a like $25 million mansion in Akron, Ohio. Right? Not too many other $25 million mansions in Akron, Ohio. I mean, I'm no expert, but I'm making an assumption here. If you were to be talking about the average home price of homes in Akron, Ohio, that one mansion is going to skew that data to the right. Most of the home prices are down around here, okay? But then you have some extreme values that are pulling that distribution in this direction. So this will get into a future lesson when we're talking about mean and median and when we use those two measures. But if you were to be looking at like real estate prices, you typically do not see an average price or a mean real estate price because that's really influenced by a skew, okay, by extreme values, possible outliers. The median, however, it's like the middle number, okay, if you remember that. We'll get into that later. Okay, but it's kind of resistant to extreme values. And it's a better measure of center when you're talking about real estate prices. Okay, it's more descriptive of the whole. Some big pictures for you. Symmetric, you see it's pretty even. We're going to be using doing a lot of work based off of this symmetric distribution. Not all symmetrics are that bell shape. Okay, we could have a mounded type of distribution like this. Okay? Going back to the symmetric, you have this peak and then it's kind of like gently balancing out on both sides where you have very few extreme values compared to the mounded where you still have relative high numbers of low and upper values. Okay. Symmetric uniform distribution, we don't see this very much in the real world, okay? But if you have even quantities going across the board, okay, the height of this distribution is the frequency. How many do you see? So if you have the same number of people with really tall heights as people with middle of the road heights, as people with small heights, short heights, okay, that would be a uniform symmetric distribution. That's not how it is in the real world. Okay? They fit more of this symmetric bell shape, where if you're looking at a homogeneous population, adult males, most people's heights are somewhere around the center. It fits this distribution. You have very few extremely tall adult males. You have very few extremely short adult males when you look at the population as a whole. Most people are in the middle. Okay. If it's not symmetric, it's asymmetric. Again, the direction of the skew is the direction of the tail. This tail goes off to the left. This tail goes off to the right. We're wrapping up here. So, that was all under the category of histograms and talking about the visualization of that overall trend. Okay? Remember that the other representation of a single variable quantitative set is a stem plot. So sometimes it's called a stem and leaf plot. Do you remember doing this like in middle school or something? Probably need a little bit of a refresher. To make a stem plot, what you're doing is you're looking at your data set and you're separating each observation into a stem, and then that's usually like a hundreds place or a tens place, and then the leaves are what indicate the individual value. I better show you an example here. Okay? So that weight data, whatever, that we had from that VCU stats course, they go through and they set the stems as the hundreds place and the tens place, and then the leaves are the ones place. Okay? So this number right here is the 130s, and this individual had a weight of 135. Okay, so you just put the 5 there on the other side of this bar. Okay, that represents the 135 weight. Okay, this is the 192 weight. Okay, for other weights that you had in the 190s, okay, we have a 195. Sometimes you'll see this separated with a comma, other times you won't. But you could put then 195 is represented by that 5 and so forth. It's good to usually have a key to identify that the stems are 10s, the leaves are 1s. The benefit of a stem and leaf plot is that it's a quick, easy way to get an idea of the distribution by hand. Okay? There are ways to make a stem and leaf plot with technology. GeoGebra does it for us, but this is not something that you typically see in like a formal report or a final report. This is usually like a quick way that you're recording survey data out in the field. Okay, you can make one of these by hand very easily to get an idea of what that distribution looks like. Here's another data set we have from 2011. All 50 states, and the percent of that state population that was born outside of the United States. Okay, so we see some ranging values here. Looks like California is our biggest. 27.1% of the population of California was born outside of the U.S. On the lower end, Alabama 3.4%, Maine 3.3%. South Dakota, 2.9. Oh, there it is, West Virginia, 1.3. I think that's the winner there for the lowest. But we could look at this data if we were to take the time. Our stems here, it makes sense to just have our single values because we're working with decimals, that the ones place would be the stems, and then the tenths place would be our leaves. So for example, this 19 stem has values of 19.2 and 19.4 for Nevada and Florida respectively. And when you have everything laid out here, you can start to see the trends. Okay? You have a bulk of data down here on the lower end. For some reason we have a big spike in the 13s. I don't know. But then it's more of a gentle slope down towards the extreme upper end. Okay, and you can see that there's a lot of distance between California's 27.1 going back to the next highest, which was 22.2. Okay, so imagine not that you're out in the field taking these measures, but you can see that general distribution. We have a lot of values down here in the lower end. You can see that pretty quickly just by hand. Almost done here, guys. Thanks for your patience. If there are very few stems, okay, meaning that you have data covering a very small range, you might see that broken down like to the lower end and the upper end. Okay, like if we had data ranging from 150 to 179, we would have 15, 15, 16, 16, 17, 17, and in our key somewhere we would designate that the first 15, represents 0 through 4, and the second 15 would represent 5 through 9, okay, and so forth for the 16s and the 17s. What that enables us to do is get a little bit more of a descriptive idea of how that breakdown occurs. That especially that might be valuable if we're looking at a stem plot of test scores for the class, right? If I just put everybody in the 90s, the 80s, the 70s, the 60s, yeah, you kind of see where you're falling in terms of the grading scale, but is everybody scoring in the upper 80s versus the lower 80s? Okay, that can be beneficial in certain situations. All right, last one for numerical data, quantitative data, is a time plot. This is reserved for showing change over time. Okay, it's like a line graph. And your x-axis is going to be the measure of time. Time can kind of be treated either as quantitative or categorical. It can really go either way, and sometimes you have an argument for either. But it's reserved for the x-axis because it's always going to be the independent variable. But you're looking for an overall pattern or trend and deviations from that trend, just like any other display. And you're also looking for patterns that repeat at regular known intervals, okay? If you're looking at changes over time, you might see seasonal variations, okay? Sales statistics might vary seasonally, okay? So you're looking for different like peaks and valleys for that reason. This is going back to that class makeup on the first day, the percent of that class that are freshmen. So we have years of the fall semester, 1985 through 1993. See that not many freshmen started in that class, but then a couple years went by, you have a higher proportion of freshmen than it dropped. Okay? You can see how things changed over time. This is a line graph, okay, time plot. This is also good for comparison. Kind of like what we saw with the bar graph. You could be comparing two or more items on the same axes. Okay? Here we're looking at average tuition and fees at universities, the academic year 1970 through 2000. We have public universities staying low, and then private universities. Okay? They kind of changed together up until right around 1980. That's when the private universities really started to take off in price. Okay. The publics were going up as well, but clearly you can see here not at that same rate of change. It's a lot of talking, but I'm done. Anybody have any questions about what we talked about today with our types of variables, categorical and quantitative, and the appropriate displays for each? Remember the categorical data, it's a label. Okay, you're measuring either the raw number of people who fit into those categories or the percent of people who fit into those categories. And you can display that with either a pie chart or a bar graph, whatever works best for the message you're trying to convey. The quantitative data, okay, where you're taking a measure, that is represented either by a stem plot or a histogram. Okay? And your idea there is you're trying to observe trends in that distribution. Okay, what does that distribution look like? It could be relatively symmetric with most of the data right around the center. Okay, symmetric bell shape, very few extreme values. We saw the other symmetric things. Don't really worry too much about that. Okay. And then lastly, we have this time plot, which we said could either be argued as categorical or quantitative, depending on how you're treating time. Okay. But again, you're showing the change over time there.